Okay, welcome to the last VQMS of the semester, everyone. We're so happy to have Eric here to present 4 different papers on using Bayesian methods in marketing. The way this works is, Eric, you have an hour to present formally. Panelists, please just unmute yourselves and jump in with any questions. Audience members, please use the Q&A box to ask questions. And then folks will stick around for a little bit after the top of the hour for a more informal discussion.
Thanks, Olivia. It's truly an honor to be here, and I want to thank the organizers. It's an amazing opportunity for me to present work that I'm doing right now, but it's also this whole idea of a virtual quant marketing seminar is just outstanding. And so this is, I have to think to myself, maybe Fred's sitting there saying the same thing, like, damn, I've been in the field for 30 years. Why didn't I think of this idea? But it's a really great one, and congratulations to the organizers. So the reason, when I was talking to Zhenling last week about what I'd present, I described to her a number of the papers I was working on, and her comment was, you seem excited about all of them. And I said, I am, that's true. And I started to think, why don't I just kind of present like a short version of each of them? And the reason I call this a Bayesian methodological assault is that all of them kind of dispel a common myth that exists to us quant marketing modeling folks. A couple of them just show a bunch of the stuff we're doing is just plain wrong, but I'll get to that. Each one, and I'll tell a story about each of the papers and how the idea came up for each of the papers. So let me just give you a sense of the 4 papers I'm going to present. The first one is actually one that's probably the most active and the most advanced. We have 2 published papers on the topic, but we have 2 or 3 more published papers that we're working on right now. I'll talk about that. This is a problem that I've been working on the last couple of years with my former PhD student, Min-Young Kim, who's now a professor at Ohio State, and my colleague, Raghu Iyengar. I'll tell you about how we got the idea for this problem, but as with all problems for me, it comes from a data set we were trying to analyze and we didn't know what the hell to do. The second one is also a problem I'm currently working on. It's a submitted paper with a former doctoral student of mine, Arun Gopalakrishnan, who's at Rice University. We spent a lot of time, Arun and I, publishing papers on hidden Markov models. It turns out that they stink. They're no good. They do great for what we call backcasting, but they do horrific when it comes to forecasting. And I'll say specifically what I mean, but I'll also say how to fix the problem. The third one is, this paper is 30 years in the making. And so it's the first academic paper I ever wrote when I was working at the Educational Testing Service in Princeton, motivated this problem. Then when I got to the field of marketing, I realized that there was a big kind of quote unquote mistake in one of the most seminal papers ever written. And I say mistake, it's not really a mistake, but it's a limitation of the model. And I'll tell you how we generalize that. And then last but not least, probably an area I guess I'm well known for is, in the homage to Paul Green and the others that did a lot of work in conjoint, is this idea now of cross-category learning, which means, for example, if I like the color red, do I like the color red for all product categories? If I like spicy Thai food, do I like spicy Chinese food too? What can we learn across product categories? So these are the 4 projects I'm going to talk about briefly. They're in a specific order that the top one is the one that's most mature, meaning we have one paper that already appeared in Marketing Science, another just got accepted in Marketing Science, and another one we have sketched out. The next one down, the HMM paper, is one we have submitted to a statistics journal, and we have another paper that we're starting tomorrow. The third one is we've done all the empirical work, and I'm going to show you the results of the empirical work. And the last one is one that we've done some empirical work, but we're literally writing up the code now to run a very large scale study. Okay. So again, as I mentioned, this first paper is joint work with Min-Young Kim and Raghu Iyengar. We call it a Bayesian dual clustering approach, but the key word here is the word selecting. And you'll see what I mean in a second about selecting data and parameter granularities. Now, if you don't like this title, here's another title. Lots of people, we've heard the term aggregation bias for years. There's been tons of literature that says, let's say you have extremely granular data and you aggregate it up to discreteness, like to the daily level or weekly level and monthly level. Lots of research in marketing has shown that your results will change depending on what level of aggregation you choose to analyze your data at. But what nobody has addressed up until us is how do you actually select the level of data and parameter granularity. And as a Bayesian, to me, that's just, if you could call it a missing data problem, but you could also call the level of data and parameter, data aggregation and parameter heterogeneity just another feature of the model that you're going to select along with standard posterior Bayesian parameter inference. So I see it as no different. I see the model as an unknown. I see the degree of heterogeneity as an unknown. I see the potential level of aggregation as an unknown. And we're going to select those at the same time we're doing our standard Bayesian inference and computing posteriors of parameters. Okay. If you don't like that title, here's the last title. All of you may think you've done model selection. Like, you know, for example, pick one of Fred Feinberg's papers. There's 15 different models in it. The one that he's presenting is the winner because it fits the best. But actually, no. You've never actually done model selection because what you've done, not just Fred, me, Hortense, Ellie, Nick, Longshu, all of you guys, is you were first conditioned on the level of data aggregation. Like, here's the data I'm going to use. And you've many ways conditioned on the level of heterogeneity. Like, I'm going to build a latent class model, or I'm going to build fully Bayesian heterogeneity. You've conditioned on those decisions before you've actually done model selection. So my point is, that's kind of not right. You need to do all of these simultaneously, and that's what we're going to talk about. So,
can I
yeah,
quickly
please.
interject? And just more of a question for you to answer later, but we'll love to hear some of your thoughts on how this framework would apply to causal inference settings. In the sense that there's a lot of data aggregation that often have to be done as a pre-processing step to deal with some sources of unobserved confounding that actually just nicely goes away, especially in a lot of time varying treatment effect estimation. And we'll love to hear if you guys are thinking about that or, as sort of how we can apply your framework to those settings.
That's a great question, Longshu. So let me just say, the amount of thinking I've done about that is not high. Mainly, I've treated the level of data aggregation and heterogeneity selection almost like a measure of model fit. In other words, I'm trying to select these, whether it's, you'll see in a second, the way to aggregate the data, how much heterogeneity to put in the model, as like, I want to sample over the posterior distribution of those features. If there's a causal inference setting, which, as a student of Don Rubin, to me, every problem is a causal inference problem. But I have not thought specifically about how this might affect causal inference in some way, or the need for other it's instruments, latent instruments, whether different observational study methods, whether it's inverse probability weighting or other methods would be more effective under one level of aggregation or another. So the answer is, I haven't thought about it that much. It's a fair and reasonable question. I haven't thought about it that much. But you're right, it is an interesting problem. I could easily imagine you'll see in a second, I could easily imagine putting either constraints or a penalty function for various things that could address your issue, but maybe we can talk about it offline. But it is a fair question.
Thank you.
Yeah, it's not the way we thought about the problem, but it doesn't mean it's not a good way to think about the problem. So maybe a nice way to say it is, since I'm always an emperor has no clothes kind of guy, not only have I not thought about it very much, it probably means our method is not particularly robust to those challenges. In other words, maybe it is. Maybe you'll tell me after the talk, oh, you've undersold it. Your approach addresses that too. I don't think so. I think we're still going to have the same challenges one would have from observational data or to make causal claims, regardless of our solution to this problem. Okay, good question. All right, so just to make sure we're all on the same page, let's just take a very simple example with a very simple data set. Imagine I have a data set with 30 SKUs. Imagine I have unit sales for each of the data sets. Imagine I have the price for each of the SKUs. Imagine I have various attributes like brands. This is orange juice. I have the brand of the orange juice. I have the size of the container. I have the material of the container, and I have, does it contain pulp or not? So this is my data set, if you'd like. And let's imagine I was going to fit a very standard log-log demand model to this data. So the log of sales is some function of log of price. But notice here there's two sets of subscripts and two different colors for color coding here. Notice there's D for data. So at what level of aggregation am I going to analyze the sales and price data? And then there's the green, an M for model. At what level of parameter heterogeneity, in this case the intercept and the slope, will I use for this particular model? So again, which level D do we aggregate the data to? And second, which level M do we aggregate the parameters to? Now, the model is completely general. So let me just say, sales and price do not have to be at the same level of aggregation. I'm just showing it that way right now. The intercept and the slope, for example, in mixed heterogeneous models or mixed models, do not have to be at the same level of heterogeneity. I'm just showing you that now to simplify the example. There's some level of heterogeneity for the sales and the price data, which is the, if you like, the observables, and there's a different level of heterogeneity for the alphas and the betas. Let me also comment that conceptually, if this was panel data, you could have a different level of heterogeneity for every person. It's a computational challenge, but it's not a conceptual challenge. In other words, as many, if you'd like, you'll see in a second, as many graphs as you want, you're allowed to have under this approach. It leads to computational challenges, again, but not conceptual ones. Okay? So these decisions are important in many settings. So maybe you're not a big fan of skew data. Okay, well, temporal data, our approach applies to. Matter of fact, I think this is the real strength of the approach. I always liked, and by the way, for the more junior scholars out there, let me say how you get your paper rejected. I can say it now because the paper's just been accepted. How you get your paper rejected is to say your method can handle any problem anytime. And so I actually think ours can, but I didn't say that when writing the paper because I knew someone would say they'll find some esoteric case or maybe some actual case that it's not true. But our method can handle temporal data, spatial data, customer data. All of these become specific cases of our Bayesian dual clustering approach. So again, don't think of skew data. That's just an example. Why is it a hard problem? So I don't know, maybe Yu Feng is sitting here saying, I don't understand why this problem is so hard. Don't we have, what about BIC, AIC, all of these methods? What about Bayes factors and marginal likelihoods? Doesn't that work? What about just simple likelihood ratio tests? The problem is, remember, these are not appropriate because in these approaches, you're conditioning on the data and the model's changing. But if I change the data, then none of these approaches apply. As a matter of fact, a simple way to think about it is, I mean, this is where the motivation to the problem started. Let's say I start with daily data and I aggregate it to weekly data. We agree that I've cut the number of observations by 1/7. Well, one likelihood now has 7 times as many observations as the other likelihood, which means the likelihood is going to favor more aggregated data just by nature of how many terms you're literally multiplying together. So none of these approaches actually address the problem. So the first paper we had to write, and this is the one that appeared in Marketing Science 2 years ago, was related. And this is, by the way, indicative of my research career. I had to solve this problem to solve the problem I really wanted to solve, which is how do you actually compare likelihood functions that actually have a different number of observations? So again, imagine a very granular data set that you aggregate up. Well, the aggregated one has less likelihood terms than the other one, but you still want to be able to select which one is better fitting or which one has a higher posterior. The problem is that you've changed the number of observations in the data. So the first, I'm not going to talk about this paper today, but if you want to read about it, it's how do you select data granularity? How do you compare likelihoods with different sample sizes? And it's something we call the scaled power likelihood with multiple weights. It's actually a very robust way to compute it. But let me show you this paper and the solution. And the solution we thought was, I know it's my own opinion. I thought it was an extremely novel way to think about it. And the idea is as a graph. So here's the idea. You take the most granular data you have, and you let each unit have its own parameter. So for example, if it's skew level data, you analyze the data at the skew level, you let each skew have its own set of parameters. For example, imagine there's N1 observations in your raw data set. You have N1 data points and N1 parameter points. So in this case, each data point would have its own parameters. Then what we're going to do is we're going to cluster the data and the parameters in such a way. And then what we're going to do is if points 1 and 2 are in the same cluster, they get summed or averaged together. If beta points 1, 2, and 3 are in the same parameter cluster, they get set the same parameter values. And so the question, what we've done is we've turned a data aggregation and parameter heterogeneity problem into a Bayesian clustering problem. So we're representing observations as points, and now we're going to cluster those points in a Bayesian way. Now, unless you were familiar with it, I wasn't that familiar with, so how do you cluster points? How do you do that? Well, it turns out the person that's written a paper on everything has also written a paper on this, and that's David Bly. He has a paper he published in the Journal of Machine Learning Research in 2011 called the Distant Dependent Chinese Restaurant Process. And so it's a probabilistic model. It's a prior distribution for how you cluster points. And actually, we modified the DDCRP of David Bly and co-authors to actually make it not only broader than the original one, but to make it interpretable, which you'll see in just a second. So again, I want to repeat, just to take a step back. I'm taking the problem of data aggregation and parameter heterogeneity. I'm going to turn data points into points in a cluster, parameter as points in a cluster, as separate ones. There's a data graph and a parameter graph. And then I'm going to cluster them using a modified version of the distant dependent Chinese restaurant process. Fred, I see you've unmuted yourself. Yeah.
Yeah, quick question. Can you just very quickly say how this is different from like a hierarchical Dirichlet process, which is usually done with stick breaking or Chinese restaurant, and it's been used a lot in marketing before? Because I think most people are familiar with that, but not this. Yeah.
Yeah, so the Chinese restaurant process has two parts to it. One is a self-joining probability. And so there's a probability I'm joined to myself, which means I remain as a point to myself. And then there's a probability I join, let's say I'm point J and Fred Feinberg is point J prime. There's some probability I join you, and it's a function of the quote unquote distance between our 2 points. So the distant dependent Chinese restaurant process, Chinese restaurant process has been around for a long time, as you know, Fred, in the field of statistics. It's a new person comes into a restaurant. Do you sit them at a table by themselves or do you sit them with somebody else's table? This is exactly that process, but it's from the bottom up. It's 2 points at a time. So I look at J and J prime. Matter of fact, one of the papers by Adam Smith and Rossi and Allenby, they have a totally different clustering process for points, which we compare our approach to. So I view ours, Fred, as a bottoms-up, point-wise, distance-measured version of aggregating points kind of 2 at a time. Does that help?
Yeah, I'm just still a little curious why it's different from typical hierarchical agglomeration things. There's a stochastic element to it, I assume.
There's absolutely a stochastic. There's a stochastic. That's a good question. Actually, so this is why it's wonderful to give talks. I hadn't even thought about this in its comparison to, I had thought of it in response to like k-means clustering, which is different, but I had not thought about it in terms of a hierarchical agglomeration process, which exactly joins points in a tree-like setting, kind of 2 points at a time, and should it be a separate node or gravity? But ours has a probabilistic nature to it. It's literally a prior distribution. on the clusterings, which is nice also. Besides, it gives you interpretability because I'm going to say which features lead to Fred and I being in the same cluster and maybe Ahmad and I being in different clusters, or which orange juices are in the same cluster and which orange juices are not. It leads to a nice interpretation. That's really valuable, but there's also stochasticity to it, and there's interpretation then of the prior. Other
Can I ask,
Please.
are we assuming this whole time that we know how to aggregate points once they're together? Like there's some correct way to do the aggregation conditional on a cluster?
Good question. So what we assume, that's, again, this is nothing I ever thought of because to me it seemed obvious, but apparently it's not. It doesn't mean it's right. If points are in this, well, let me take to the parameter side first, because that I think is easier maybe. If points are in the same parameter cluster, they are given the same value. So for example, in the example I gave, if skews 1, 2, and 3 are all in the same parameter cluster, they have this, there's one set of parameters that governs all three. The data cluster, we just assumed that if points are in the same cluster, they can be aggregated, which means summed or averaged. It doesn't matter which of the two. That's the first paper addresses that. We just assumed that they would be summed or averaged, just like you would sum days to a week, you would sum weeks to a month. If you had counties in a region, you would aggregate those counties just like you would do naturally with data you had when you aggregated that data. But if you're asking me, could there be some weights you could potentially apply to different observations? I guess that would be an even more generalized version than we've addressed. We've only addressed the issue of, I'll call it a simple aggregation process once points are in the same cluster. Okay. All right. And just to let you know, there's an interesting issue here. So this turned out to be a computational contribution, but you don't have to do it. And what I mean by that is, I've written papers actually with a former doctoral student, Andres Musalam, and my colleague Jagmohan Raju on Bayesian estimation with aggregate data. We put a restriction on this set of papers that the data has to be at least as aggregated as the parameters. In other words, conceptually, like if you think of BLP, you have more aggregated data and disaggregated parameters. We're actually not allowing for that in this work. It doesn't mean you have to impose it. We actually did it because we thought it made sense for the kinds of problems, and it led to a neat computational contribution, which is what we're calling a split and merge sampler. So for example, let's say at a given iteration of your sampler, you have points 1 and 2 and 3 and 4 joined together, okay? Now what we're going to do is we're going to potentially split them up. We don't have to. Like, for example, you see 1 and 2 stay together, 3 and 4 get split. So you split data, then you take that split data and you put it into the merge step for the parameters. Maybe you merge them, maybe you don't. But this split and merge sampler guarantees that the data will always be more heterogeneous than the parameter clusters are. Now, again, we didn't have to do this. The part that was neat about this is it actually gives insight into the thing I'm going to talk about on my last slide on this paper, which is how do you bring in any set of constraints? And so, matter of fact, why don't I just talk about it now, and then I see Ellie unmuted herself. I'll take a question here. We're actually going to use this idea to assess the economic loss potentially of privacy. So you could imagine imposing privacy constraints where only a certain number of data points, like it has to be at least 15 data points in a cluster. Or I could never divulge the following. We can then put that as a constraint in our Markov chain sampler, rerun the analysis, and then easily see the impact of those privacy constraints. So what we've done is we've actually compiled a list of about 30 to 40 papers in both marketing, economics, computer science that have addressed privacy in different ways. And through our merge and split sampler, we're going to be able to address a number of those issues. But let me get to Ellie since I see her unmuted.
So maybe I missed something in the setup, but is there any kind of regularization over the parameters or just independent priors on each of them?
It's a good question. So it's a standard hierarchical model. So there is regularization over the parameters. And so, but you are right, Ellie, that as you join clusters of parameters together, the degree of regularization changes because now, like you can imagine a fully heterogeneous model with N1 parameters, and then there might be a hierarchical model and it gets regularized. But if some of them get bunched together, then all of a sudden the number of parameters changes and potentially the hierarchical structure changes. Another thing I should mention is we're not assuming that as the level of data aggregation changes or parameter aggregation changes, that the functional form of the model has to stay the same. Like for example, let's imagine you just had binary data 0, 1, and you're going to model it through a logistic model. Well, the minute you aggregate that to a count, obviously a logistic model doesn't apply anymore. And so in the paper, we're calling the parameters theta. The probability distribution depends on D and M, which are the level of data aggregation and the level of parameter aggregation. And to Ellie's point, the hierarchy, the regularization may change as a function of M.
I was actually worried about, or thinking about, not really worried, when you do this parameter clustering, if you were really heavy-handed with the regularization, you'd get a different set of clusters, right?
I think that's absolutely right. And so I think it's fair to say it's not unrelated to Olivia's point, which is you're making like there's no question if you look at the directed acyclic graph that emerges from these, there are conditional independence assumptions being made. Certainly depending on what types of hierarchical prior you put on things. Matter of fact, a separate problem I'm working on now is something called the complexity prior. Depending on how you could actually put a prior on the degree of complexity, like you could put a prior on how many clusters there are and how do you do that. All of that, no question, could have an impact. And maybe it also relates to Fred's earlier point. I think it's fair to say that this work is, and it's not, given who I am, it's heavily parametrically identified. I think that's a fair comment and a fair criticism. This is not a model-free approach. It absolutely depends on how you select the distance function, which variables you put in, exactly what functional form, how you construct the hierarchical structure. I think those are all fair comments and criticisms. Okay.
Eric, there's a number of comments from the audience. I'll try and summarize.
Sure.
Minho was asking, how can you think about deciding on aggregation by just considering homogeneity in things like prices and promotions for applications like pricing? Put differently, why don't we just aggregate up whenever x variables are the same?
Yeah, so it's a good question. So we got a lot of questions like that in the review process. Which is, doesn't sometimes the substantive nature of the problem make it so that certain levels of aggregation make sense? And the answer is, the good news is, there's nothing that stops us from fixing one of the two graphs at some level. As a matter of fact, a special case of one of these, if you think about a latent class model, the data is the most granular and you model the parameters. There's all kinds of ways to think about it. No, I don't have a problem with thinking about are there ways to aggregate prices that could be consistent with the process? No, I think that's a fair question. We did actually spend a lot of time thinking about, maybe it relates to the question that was asked earlier, is there a theoretical justification for the clusters that are made? And I would say the answer is probably no. And maybe this relates to Long Shu's earlier point about endogeneity or other things about causal inference, depending on the level at which you aggregate the data. I think that's fair.
Yeah, and similarly, Adam Smith is asking, how does the objective function of the analyst, sort of like, am I pricing individual products, product lines, et cetera, relate to the decision on how to aggregate your data or parameters?
Yeah, good question. So first of all, I want to thank Adam both for being generous with his code and his work, because our work directly builds on a lot of the work that he had done. The answer is yes and no. I was about to say something I'm not sure I believe, which is if you're going to price something at a certain level of aggregation, you certainly may not want to aggregate it above that level of aggregation, with one exception, which I'm going to get to in about 2 slides. So I was about to say the problem you're trying to solve has an impact on what level of aggregation you should be thinking about here, or even what the feasible set of plausible aggregations are. Like, for example, you might say, like, I'm a business, I have to price at least, I have to put prices on SKUs. So, all right, well, if that's true, then maybe you put an upper bound on the level of aggregation. You say anything more disaggregated than that is fine, but anything more aggregated than that is not fine. This approach can easily handle that.
Thanks. One more quick question, which is Remy's asking how this compares to literature on factor analysis, where we think about creating factors from sets of disaggregated inputs.
Yeah, so factor analysis makes obviously an assumption of these kind of latent inputs. Certainly, you could do a Bayesian version of factor analysis. I think well, maybe this is another way of, since good question, Remy, not surprising. It's always nice to hear from you. I would say the following. In a factor analysis, there's not hard coding, right? You have weights that are put on how variables are combined or load on different factors. Here, maybe this also relates, Olivia, to your point, like it's hard coding. You're in a cluster, you're not in a cluster. Now, let me just say, we're sampling over the posterior distribution. We're bringing that form of uncertainty in. But if points are in the same cluster, they're in the same cluster, they're treated as homogeneous, whether it's in the data cluster or the parameter cluster, there is no, if you'd like, partial weighting like in a factor analysis type approach. So that would be my answer, is hard coding versus, I'll call it, weighted factors.
Eric, I have another question.
Oh, sure.
So is there a limitation, or is it totally fine if there are effects across units? So I'm thinking, for example, in a temporal setting, if you have long-term effects, and these long-term effects last for days, the moment you aggregate them by months, then some of these effects may kind of go away, or you move from a first-order Markovian structure to a k-order Markovian structure.
Yeah, absolutely, Nick. That could absolutely happen. And I would say the best way to think about it, and we spent a lot of time thinking about that. I'll answer you in two ways, maybe three. The first one is we recognize that, as a matter of fact, in the original paper we wrote in Marketing Science, it was an AR structure, and depending on how you aggregated the data, the AR structure absolutely changed. So we recognize that the probability distribution for the data, once you aggregate it, may change the parameter structure entirely and even the model entirely. So if you'd like, the probability distribution P depends on theta of D and theta of M, how you aggregate the data and the model. So that is 100% true. Second is, we treated your comment, like one could treat your comment as critical. We treated it as a positive. And here's what I mean. Someone could say, well, why wouldn't you ever want the most granular data? Well, it turns out that you may actually average out effects and average out unobservable effects if you aggregate the data upwards. Like an example would be at the monthly level, you don't need this AR structure, but you need it if it's at the daily level. So we viewed that as a strength of the approach, that in some sense, for getting better predictions, both in sample and out of sample within a given model class, things could actually improve by aggregating and simplifying the model. I see Fred's hand back up.
Another quick one. Does this presume that there's some type of plausible or canonical metric on the space of the data, or can you handle categorical data, for instance, by using data augmentation approaches and impose that metric on the data?
It's a good question. So the answer is it could handle, I mean, if I want to say it this way, and we can talk about it offline, Fred, it's a good question. If you can write down the likelihood for the data, you can apply this approach to the data. And then, but you're also asking something about a distance between data, which is different in a categorical space. But the distances, by the way, are not on the observed data Y. So that's where it's a little bit different, but we can talk about that offline. Okay. Let me just quickly, just to say, I'm just going to put all this up there at once. We applied it to a very large data from the Nielsen data. You can see here 332 SKUs, 61,000 observations. Let me just comment on one thing. I'm not going to talk about it today, but one of the questions that was asked us in the review process is, how large a graph can you handle? And the answer is pretty large. Like, I don't know the upper bound, but we actually thought we developed this, but then of course we found out that of course thousands of people had done this before us. You actually don't need to update every graph at every iteration of the sampler. We called it mini batch sampling. Apparently that's what computer scientists call it too. Let me just say that we're able to handle larger graphs than you might think. Just to let you know, we fit a log-log demand model here. You can see we have log of sales and log of price, log of display, log of feature. Notice again, sales, price, display, and feature have a subscript D for the data graph. The parameters, gamma 0, 1, 2, 3, have parameters that relate to M, the model graph. Just to show you a quick picture, these are the posterior distributions of the weights, which is how likely are two objects of the same type to be in the same cluster. So for example, the one on the left is the data graph, the one on the right is the parameter graph. So you can see here, brand seems to have a big impact on which data points get grouped together. Module, material, size, less so. These are actually the posterior price elasticities, and we compute in the paper. I'm not going to show it to you today, the optimal prices under each. The picture on the left is our method. The one on the right is where we fix the parameter graph at the most granular level, but only cluster the data. The one on the right is where we fix the data at its most granular level, but only do latent class. And again, it turns out, in fact, we've run this on a bunch. It turns out our approach is always in the middle. Like, I always describe it as the variation has to come somewhere. So if you keep the data very heterogeneous, but fix the parameters, the source of variation goes somewhere, and the opposite is true as well. For the if you cluster the parameters but fix the data, it has to go somewhere as well. Okay. This was the one thing I wanted to make, and this was, I thought, the most important empirical finding from the second paper. Let's say imagine Nick wants to make a prediction of monthly sales in the future. What many people historically have said is, well, all right, so what I'm going to do is I'm going to fit a monthly model to the data and get a prediction of monthly sales, and I'll do the best I can out of sample. What our approach says is you might actually do better by aggregating the data upwards, make a prediction at the quarterly level, and disaggregating it downwards after making your prediction. And so what we were trying to address here is sort of related to the question that was asked, which is your question of inference or your topic of inference. Let's say it's monthly sales or quarterly sales. That doesn't mean you have to fit the model at that level to get the best predictions. What you want is the optimal, if you'd like, combination of model fit. You want to fit the best model, then forecast, and then either disaggregate it up or disaggregate it down. And we show this in a number of different settings in the paper, which we thought was quite counterintuitive to people. And last but not least, just to quickly say, the next paper that we're going to be working on is the cost of privacy. And so you could easily imagine putting restrictions on the clusters, both on the data side especially, but maybe the parameter side, that actually allow us to say, how much do you lose by having to keep, a certain minimum number of data points, or by adding stochastic noise? All of that can be addressed using our approach, and we're very, very excited about that paper as well. So let me stop here for a second just to see if there's any more questions about this paper before I move on to the hidden Markov one. Okay, so let me talk about the next one, which is backcasting versus forecasting. And this one may surprise a lot of people. So let's take a look at the following data set. As a matter of fact, let's call this an actual data set that Arun and I were working on. We had data from a financial services institution about someone's bank balances. And let's imagine you look at this data set, and I think it's not hard to believe that this could be fit well by a two-state hidden Markov model, where you see one stated about a value of 1, the other stated a value of 4, and we're oscillating back and forth between the low state of 1 and the high state of 4. Okay, seems pretty reasonable. Okay, and let's imagine I'm sitting here at date 45, the end of the data period, and there's no doubt if I try to fit a hidden Markov model to this data, it will fit extremely well. We call that backcasting. Okay, now here's what, remember, I'm sitting here at day 45. Here is my data. I now want to forecast going forward what the person's bank balance is going to be. Okay? Here it is. This is what you get from a hidden Markov model. It's mean reverting from the last state. And I'm sure Fred probably knew this already, but there's only a certain number of shapes you can actually get from the predictions of a hidden Markov model. They're based entirely on the eigenvalues of the hidden Markov model. And actually, it's a very limited number of shapes. And by the way, I have it going from low to high, but you can just flip it over. You can also get the reverse depending on whether you're at the high state. So hidden Markov models are very limited in the number of shapes that you can actually get for predictions from them, mean predictions. Let me also comment on adding more states doesn't help. So maybe Ellie Feit says, well, how about a 3-state model? Does not help. How about a higher order Markovian? Why only a first order? Does not help. How about, I'm a colleague of Pete Fader. Why don't we make it a bi-die model? None of these help. A bi-die model is just a hidden Markov model with an absorbing state. So that doesn't help. So none of these help. Okay. Now, what moderates the error? Can I ever do well? Well, the answer is you can if you get lucky. I mean, if you look at this curve here, on the x-axis here, I have the probability of remaining in a given state. Well, obviously, if I stay in the last state I was in, I'm going to get very little error. And notice the error gets maximized at about a half when you're more uncertain about if you're going to flip back and forth between states. And so it turns out, and just to make sure we're all clear, I want to draw everybody the picture. I showed you the data. I've now fit the backcast. That dotted line past data point 30 in this case is the forecast. That's the forecast you get. And by the way, I tricked you. This data is actually not from an HMM. It looks like it was from an HMM, but it wasn't. That's also part of the purpose of this paper. And just to show you how to fix this problem, it turns out, and there's actually a much more general class of models than an HMM. There are what are called mixture autoregressive models. I've now fit a mixture autoregressive model to that same data set. I want to go back for a second. It looks like an HMM data. And by the way, if you stopped at period 30, you would declare victory and say a 2-state HMM. And then the minute you got a forecast, you'd get that dotted line. This is a more general autoregressive mixture model, which fits the data better. Okay? So let me just stop there and see if there are any questions about the HMM paper. So our point here was a couple. Number one, HMMs backcast extremely well, but they're very limited in terms of forecasting. Something I didn't put on a slide, you could get lucky. Now, what do I mean by that? If you happen to have X's that map the pattern of the data out of sample, you could get lucky in that if you have all the X's that are in the generative process, you could actually get the right pattern. But if you have omitted X's or something like that, the hidden Markov model is not going to help you. So our point is it does well for backcasting, not great for forecasting, but there is a more general class of models that if you're interested in forecasting will do better than an HMM. Okay. Let me just see if there's any questions here. Okay. We go to the next one. So this is a joint paper with one of our PhD students, Fei Wang. She's joint between psychology and marketing, and my colleague in psychology, Sudeep Bhatia. So let me say where the idea from this paper came from, and then, well, it came from two places. So the first paper I ever wrote was in 1994. I was at the Educational Testing Service in Princeton, I was in their statistics research group. And I was working on a problem on educational tests where I was trying to understand the properties of adaptive testing, which means, this was the first year that ETS brought tests online. The idea is if someone it's kind of like adaptive conjoint. If someone gets a question right, you give them a harder question. If someone gets a question wrong, you give them an easier question. And that was the basic idea, was that you'd like to maximize the information gained from every single item. And I was working on the problem, and I kept getting this very, very strange result. It's what I called negative information. And what I mean by that is that my posterior variance for a test taker after observing test items would go up, not down. I want to say it again. I collect data and the variance goes up, not down. First, I thought it was a programming error because I was doing Newton-Raphson to find the mode. It was not a programming error. I then did the mathematics on it and showed that it actually holds for this model called the 3-parameter logistic model, which is a mixture model. It does not hold for something called the 2-parameter logistic model, meaning you cannot get this fact for the 2-parameter logistic model, which, by the way, 99% of all educational data is fit using the 2-parameter logistic model, which means that no matter what item I give to Fred Feinberg and no matter what his answer is, my posterior variance is going to go down. And my point is that's wrong. So in 1996, I got to Wharton and I read a paper. Someone said, you must read this paper. You must read Erdem and Keen. So I read it. It's like, wow, amazing paper. And it's got the same wrong assumption. And here's what I mean. So this is the paper. Let me lay it out. Let's imagine I have a prior distribution for a parameter theta that's normally distributed. Let's imagine I have a likelihood function for the data that's normally distributed. This is the classic normal Bayesian learning model, right? This is the posterior distribution, standard completing the square. Posterior variance is always lower than the prior variance. It's a fact of the normal model. No matter what information signal you receive, the posterior variance is lower than the prior variance. In other words, learning always happens. Now, that bothered me. It bothered me because of my work 28 years earlier, or it bothers me today of my work 30 years earlier at ETS. But here's an example. My favorite restaurant in Philadelphia is Vernick Fish. By the way, next time any of you are in Philadelphia, I'm more than happy to go with you to Vernick Fish. Ellie's a Philadelphia, and she would agree Vernick Fish is an excellent restaurant. The food is really good. Matter of fact, my prior on it is that it's my favorite restaurant in Philadelphia. Let's imagine Ellie and I go there for dinner, and the food sucks. Well, Erdem and Keen, posterior variance is lower. Bradlow believes the posterior variance is higher. I'm less certain how good the food is. It will not allow for that, the normal model. The normal model will not allow for increasing variance. So here's what we did. Very simple extension. We take the normal model, and instead we fit a mixture prior. So now my prior is going to be, let's just say, the mixture of two normal components. My signal is the same as before, is a normally distributed term. Now I get a posterior variance, but now you can get increased variance. And there's two conditions under which you can get increased variance. One is what we call increased balance, meaning the two hypotheses, it's good or it sucks, move more towards 50-50. Or you get greater polarity, which is separation between the two modes. Both of those can lead to increased posterior variance. Now, what did we do about this? So here's what we did. We've run a bunch of experiments. We measured people's prior beliefs. We've presented them information, and we've measured their posterior beliefs. We've done this for a whole bunch of different product categories. We've measured their prior beliefs in given ways, posterior beliefs, all kinds of stuff. We actually used large language models to present people information with a certain degree of valence, which was kind of fun to do. But here's the key table. If your prior is positive to start with, and I show you positive information, or your prior is negative to start with, and I show you negative information, our result subsumes the standard normal Erdem and Keen Bayesian learning result. However, if the information you receive is incongruous with the original information, you can get increased variance. And that's what we wanted to show. The mathematics shows us, and the other nice part about it is we can show which mechanism is it. Is it because you're getting increased polarity or you're getting increased weight balance? We can actually test for those two hypotheses by just fitting a mixture distribution to the prior, a mixture distribution to the posterior, and see which way things are moving. So just to show you the results of 3 early studies that we've done, you see 2 of these are restaurant, 1 of these is wines. On the x-axis, I have the degree of information divergence. How much does the likelihood information differ from the prior information? And we can see on the y-axis is the change in variance. As the information divergence increases, the amount of change in variance increases and goes up. Each data point here, by the way, is a different subject. We've also done the same thing here for confidence is on the y-axis. You become less confident if there's information divergence. You can see here. And the other thing is you get greater choice deferral, meaning you could think of a utility function as having a mean component and an uncertainty component. People become more uncertain, they become less confident, etc. Okay, so let me just stop here and just see if there are any questions about this research. So I want to say again, the idea originally came from this paper from the Educational Testing Service. I realized that a mixture model could have this property of increasing variance, but a single unimodal model could never. Normal model can never give the result of increasing variance. I then saw Erdem and Keene. I saw they had a normal model for information signals. I thought, well, let's just fit a mixture component. We ran some behavioral experiments now. We show that actually variance can increase, and we can show for what type of people it increases, under what setting it increases, etc. But the good news is, in some sense, we can also test the null. When the posterior variance should go down, it does go down. Okay.
Eric, just a quick clarifying question.
Yeah,
did you survey their uncertainty of the subjects?
We did. So just so you know, let me see here. Maybe I didn't show. Oh, yeah. So the y-axis, Yufeng, in the left-hand graph is, so we measured all kinds of things. Matter of fact, we measured willingness to pay. We wanted to see if that changed. We measured choice deferral. We measured their certainty in beliefs. Now, of course, part of that certainty, Yufeng, we can ask them about, which we did, but some of it, they actually drew their actual distribution. So we can compute the variance of that distribution as a measure of uncertainty as well.
Oh, that's interesting. Thanks.
So we've collected all kinds of DVs, if you'd like: deferral, willingness to pay, choices, uncertainty, confidence, just trying to make sure that we kind of have a consistent measure of the effect. Other questions? Okay. Let me just, in the last 8 minutes I have time, it's going to work out perfectly. Let me just talk about this problem of Bayesian cross-category learning. This is with a current doctoral student of ours, Raquel Chuli, and my colleague, John McCoy. The idea for this one came, this was about 4 or 5 years ago. I was doing a consulting project, I should call it, with Procter & Gamble. And they obviously make a bunch of consumer packaged goods. And obviously, it's not surprising, P&G runs lots of conjoint studies. And so we were going to run a conjoint study for a new product category. I don't remember exactly what it was, but I started to think, I wonder if we have to even run this. Like, haven't you run like 5 trillion conjoint studies in the past? Like, can't we just take the partworths of those conjoint studies and learn what the partworths are going to be for this new product category or this other product category we've never run a conjoint for? Like, if we know how much people like spicy, don't we know that? And, the question is, how category specific are preferences was the question we wanted to ask. So just to show you, I've also sometimes called this paper 2-for-1 conjoint, which is, can you literally do a conjoint in one product category but learn preferences for another product category? Okay. My other comment on this is I can't believe no one's done this. Maybe there's a lot of people on this call that'll correct me that someone's done this. I've never seen a paper that's done this. It doesn't mean it hasn't been done. I've never seen a paper on this. But let me just be very specific. Imagine you were going to run a conjoint study on hiking jackets. So let's say for now pairwise conjoint, but it doesn't matter. I show you these 2 hiking jackets. I ask you to pick A or B or even a no choice option. That's fine. You pick which one you want. Okay. Here's another pair. You pick which one you want. And of course, we're going to estimate the utility of a hiking jacket as the covariant vector of the hiking jacket times the slopes of the hiking jacket, right? And beta is what we're trying to learn. We're trying to learn what these slopes are. Okay. Now, imagine instead I show you sleeping bags. And I'm going to ask you to make choices between the sleeping bags. Okay. Now, for this simple example, it's not true in the current version of the paper. So now, well, this is true in the current paper. Now I'm going to estimate the utility of sleeping bags. I'm going to use the X's for sleeping bags, but I'm going to use the beta for the hiking jackets. I'm literally going to take the partworths I learned from this study and directly apply them to this study. Now, what we haven't restricted going forward is for this study we ran here, they had to have the same attributes and levels because I actually need a vector of partworths. But we've actually generalized that now. The other thing is, I'm going to use the partworths from a different study, or to be honest, the posterior distribution of partworths from a different study to estimate the utility of sleeping bags. And I never did a conjoint of sleeping bags, just to be clear. Now, by the way, there is another form of thing we talk about in the paper. Imagine you still want to do a study of sleeping bags, but you wanted to cut down the number of observations. You can do that. Imagine you wanted to do one of sleeping bags, but you want to do less pairs to show people. We can do that. There's lots of other ways besides I'm not going to do the sleeping bag one at all that could still be beneficial for the company. Okay. Now, let me show you what I'm showing here. We actually did do the conjoint study for both. But just to be clear again, when I'm computing the posterior distribution for sleeping bags, I did not use the sleeping bag data, but we wanted to measure the truth. This shows you, every dot is a person, shows you the posterior mean for sleeping bags and partworths, where, again, a 45-degree line would say they're the same. And this, by the way, was a within subjects design, so I have the same observations for each person. And you can see everything's very, very, very close to a 45-degree line. And we've now run this. And by the way, 20 HJ stands for hiking jacket against a hiking jacket. SB stands for sleeping bag versus sleeping bag. 20 is how many observations we collected, how many pairs we collected on each person. Okay. And just to show you, what this represents is the market shares of each. Like if we don't care about partworths, but we really care about the prediction of market shares of each, like how much would a future product have, we show you, it actually turns out here that they have the same rank order except by one. So pretty much the same rank order of the two sets of products. Okay. And I'll wrap up with this and then just see if there's any more questions. The next project I'm working on, I've been sitting on for 20 years. I'm looking for a co-author if somebody wants to work on this as well. I'm calling this negation conjoint. So why do I have to pick the object I like the most? Why don't I eliminate the ones I hate the most? And I could easily imagine a scenario where that's actually more predictive than picking. So I'm removing objects, I'm not selecting objects. And so I have a conceptual framework for it. I haven't collected any data for it yet, but I think it's another, and the nice thing about this one is you literally wouldn't have to change the software at all. Instead of modeling the one you pick, you model, let's say it's choice-based, you're modeling the one that gets removed. And so it would literally just require you changing the words and maybe you would get better predictions. Okay. So I'm not sure what kinds of, what's common among these problems. Except I'll wrap up with this. The first project was, again, Min Young, Raghu, and I. We had a data set of app usage. We just didn't know how to analyze it because we didn't know what level of granularity to use. That's what made us think about it. Arun and I fit the second one. We started fitting these models and started looking at predictions, and we noticed the predictions were really bad, and we wanted to know, was it us or was it just something about hidden Markov models? The third one was, again, back from my ETS days, I was just interested in how people learn posteriors going up versus down. And the last one was just a practical problem. I was trying to see if I could save companies money by maybe not having them run conjoint each and every time. So I'll stop there and see if there are any questions that people have.